Hello students. In this lecture, we shall discuss about the digital signal processing hardware units. So which hardware units are responsible for the more efficient operation of digital signal processors? The first hardware unit we will discuss about is called as multiplier and accumulator. It is called as MAC. Now, as we had discussed in the past, there are numerous applications in DSP where we have to do repeated arithmetic operations. The problems like filtering, convolution, correlation, FFT, etc. will involve repeated multiplication followed by addition. Therefore, it is advantageous to have a dedicated unit to perform the operation of multiply and accumulate. Now, in comparison with the general microprocessor, which is based on the von Neumann architecture, the digital signal processor uses the MAC, that is a special hardware unit for enhancing the speed of digital filtering. Now, this dedicated hardware and the corresponding instructions that are provided for accessing it, these are collectively called as MAC operation. The basic structure of MAC can be seen from the diagram here. This example considers two operands which are stored in the respective registers, which are called as X register and Y register. The operands here are believed to be of 16-bit size. Now these two 16-bit inputs are fed to the multiplier, which results in a product which is of size 32-bit. If the input is of size n-bit each, result will be 2n. Then this answer is provided to the block which is called as accumulator, where the operation of addition happens with the previous result. So whatever answer we had in the accumulator previously is passed on to what is called as result register, from where it is fed back to the accumulator. So this block is responsible for adding the product generated from the multiplier to the previous value of the accumulator. So the operation of multiplication is followed by accumulation. While the multiplier performs the current multiplication, it can go with the addition for the previous instruction. Hence, the operation of multiplication and addition, previously requiring one cycle for each separately, now can be performed within a single cycle by going with the parallelism. The output, which is said to be a double precision data, is the result which is there in the accumulator. The next block we will consider is called as a shifter. In digital filtering, in order to prevent the condition called as overflow, we require a scaling operation. In simple words, scaling down operation is accomplished by shifting the data towards the right, whereas scaling up operation can be performed by shifting the data towards the left. One unit of shift towards the right is as good as dividing the number by 2. One unit of shift towards the left is as good as multiplying the number by 2. Now let us consider some simple examples. For example, if you have a 3-bit data word which is 011 in binary, its equivalent in decimal is the value 3. Now this value, if it is shifted to the right, the result becomes 001. The one which is there in the LSB position has moved out, and the new value which is inserted from the left side is the value 0. Now this decimal equivalent is equal to 1. Now this answer can be verified as 3 divided by 2, because you're shifting to the right by 1 unit. So we are dividing by 2. 3 by 2 is 1.5, but 1.5 is the truncated result. Okay, 1.5, the answer exactly we don't get. We get the truncated result of 1.5 and the result you get is 1. Okay, so although I'm expecting the answer to be 1.5, the answer we are getting after truncation is 1. Now, if the same number is shifted to the left, then we will get the number as 110. So 0 is inserted in the empty position on the right. And the equivalent of that in decimal is the value 6. Now, this is same as taking the value 3 and multiplying it by 2. Now, the digital signal processor often shifts data by several positions. It's not true that we'll do only single bit shift. We may do shifting in several places at a time. Now, irrespective of the number of places, the time consumed for this shifting operation is said to be only one single cycle. Hence, having a dedicated hardware called as shifter will definitely speed up the operation of performing the shift. So hence, the scaling operation, it is incorporated in the digital signal processor architecture. The next block in consideration is called as an address generator. The need of an address generator in a digital signal processor is to generate the address for the next data on the data buffer to be processed. Let us first understand what is the need for a data buffer. As we realize, data may be arriving at a uniform rate or data may not be arriving at the same rate. Now, when data arrives at different instants of time and we have to process data in the form of blocks, we require some sort of storage. Now, this sort of storage mechanism can be implemented using what is called as a buffer. Now, if you are implementing a linear buffer, that means that if you are saving the data as and when it is arriving in a continuous fashion, linearly, then probably we may run out of memory. And there is a possibility of the data overwriting some content in memory. Hence, there is a need to restrict the size of memory. Now, this mechanism can be done in a very simple way by going with the circular buffer. The concept of circular buffer is very simple. Once it starts storing, the circular buffer has a starting point and it definitely has an end point. You start saving data in a sequential manner. As soon as you reach the end, you again start from the very beginning. That means that the data that was the oldest one is the first one to be overwritten. Having a circular buffer puts a restriction on the number of memory locations that you will be requiring. So with the finite number of memory locations, we can reuse the same memory location again and again and store the data. Now, here we get an impression that the old data will be lost. Please understand that in real-time applications, the validity of the data is expired once the data is old. That means that the data, once it is old, it really doesn't have any importance. So it makes perfect sense to overwrite the content which was stored a long time back. Okay, so this concept utilizes the same idea. Now let's discuss the idea further. The basic mechanism of circular buffer is as shown in the example. The example considers that we have 8 data samples. Now in a circular buffer, we use a pointer. The job of the pointer is to point to the newest data sample. So in this figure, we call x of n to be the newest data sample. Now after x of n, the next sample, it will be saved in the location called as x of n minus 7, because this happens to be the oldest sample and this value needs to be pushed out. Hence, the location x of n minus 7 becomes the location for the current new sample. The original location for x of n now becomes the location for the past sample x of n minus 1, and the process continues, and at a time only one location is updated. So this is the principle behind the address generator. Address generator is responsible for pointing to the correct memory location. Whenever we use circular, we have to implement the concept of mod. So this involves circular addressing as well. Continuing the example, the circular buffer here acts like a first in, first out buffer. The item that was stored first will be the one to move out first. Each datum on the buffer does not require to be moved. The figure here is a situation where we are assuming a 2-bit circular buffer. When you are using 2-bit address, we can access 2 to the power of 2, 4 different locations. So here the locations are named as A, B, C and D. So these refer to the data that is coming out of the ADC or analog to digital converter. Now the job of the circular buffer is to maintain the values and to store new values as and when they come. So the same concept of circular buffer, you can observe that the pointer is pointing to D, illustrating that D is the latest data which we have placed. And along the circle you can see which are the past data values. Okay, so D is the newest sample, followed by C, followed by B and A. So A will be the oldest, D will be the newest. The same concept is illustrated on the right by using what is called as a FIFO buffer. So in the FIFO buffer we can see 4 memory locations having the value A, B, C, D. D is the newest data and hence it is pointed by the pointer. If a new data, that is E, is arriving, then the E will obviously override the oldest data which was found in A, and the updation required here is only one memory location. So what we observed here is that only E is changed in place of A, and the pointer immediately points to the location called as E, and the rest will be called as the past values. Now the same in the FIFO queue will have E on the top, followed by D, C and B. A has obviously moved out. Let's imagine that there is one more data which is arriving. It has a name called as F. When F arrives, the oldest data in the queue, which is called as B, is overwritten and the pointer is also updated. Now the sequence is F, E, D and C. So always we observe that the newest data will be on top of this FIFO structure. Now in examples like FIR filtering, the data buffer size can reach several hundreds, and hence it makes perfect sense to use a circular buffer, which will definitely enhance the processing speed. Let us take a look at the common digital signal processor manufacturers. Now, digital signal processors, they are classified as general DSPs and special DSPs. The general DSPs are those which are designed and optimized for application such as digital filtering, correlation, convolution, FFT, etc. Meaning that they are not actually meant to do one task, but they can carry different tasks based on how you program it. Now the facilities available on the device, since it is general, it should have certain amount of features catering to different needs. So you can expect a little bit of everything, but you cannot expect a lot. Now let's go to the other category. It is called as special digital signal processor. Now, why it is called as special? Because it has been designed for a particular application. That means that the architecture here is optimized for a unique application. For example, audio processing, compression, echo cancellation, adaptive filtering, etc. So this is a dedicated device. Now, in the rest of the module here, we focus our attention only on general digital signal process. Coming to the manufacturers, there are some major manufacturers in the DSP industry. They are Texas Instruments, Analog Devices, and Motorola. TI and Analog Devices, both they provide DSP families belonging to fixed point as well as floating point. Motorola, meanwhile, concentrates on fixed point DSP families. For study purpose, we shall just consider the TI families, discuss about their architectures, and study some real-time implementation using the fixed and floating point formats. Thank you all.